Perfect. Okay, let's see. How can they see us? One moment. Let's make sure they have us in Paris here before we go.
Okay.
All right, we're all ready to start. Thanks everyone for your patience. It's great that we can do these remote. I really appreciate everyone being patient with us while we make this work. Okay, so Gordon, please take it away whenever you're ready.
Okay, well, thank you very much. So this is joint work, as you can see, by Adam and myself, and the title tells it all. So contextual source code transformations, the idea is that you transform two contexts, and you want to do that because you want to do reverse differentiation. So if you've got two programs, P and Q, and they give you context C and D, and you want to go backwards, you can substitute C and D or D and C, which according to how you want to go. I already talked about this in Paris in June. And since then, I wanted to figure out how to extend it to a more expressive language, in particular adding sum types. And sum types are a lot of fun, because the sum types are basically simple manifolds. So you can think of sigma plus tau, it's a manifold, a disjoint manifold, and you have more than one tangent space. At sigma, there'll be some tangent space, and at tau, there'll be another tangent space. So your tangent spaces are dependent, so you need dependent types. This idea has been kind of around for a while, but Nunes and Vakar were the first people to really make something of it. So let's go to some details, and obviously what I just said will be repeated. So the idea is we want to look at three things: reverse differentiation, forward R there, forward differentiation at the top F, and transposition. And reverse differentiation is transposition after forward differentiation. That diagram commutes, and by commuting, I mean it really commutes. If you take the source code in the source language S and you do forward differentiation to the target language T, and then you do transposition, you get exactly the same code. So in terms of efficiency, and I care about efficiency here, you get just as efficient code for reverse differentiation, whichever way you go through the diagram. For efficiency, you want to work on a-normal forms. So that's the a-normal forms of the source language. You translate to the a-normal forms of the target language with forward differentiation, but reverse differentiation and transposition, which has to go backwards, has to translate to the context. So I think I've probably said everything on this slide. Oh yes, so but in order to do reverse transposition, you need to know where the linear parts are. So T is a mixed linear nonlinear language. So I guess that's all about that. So on the next slide, something about advantages. Because we do a reversal of computation at the meta level by using context, we don't need to do it at the object level of the programs. So everything here is first order, unlike other pieces of work which use higher types or control flow operators in the target language. We don't need any of that. Everything's first order. And they're all defined by simple structural induction. FT, as we'll see, it's a more or less standard forward differentiation program. The only thing different is it keeps track of the linearity as it does its job. And I've already said the last part, and I've already said the second last part, so that's good. In terms of efficiency, I won't go into any details in the talk, but the headlines are that, excuse me, the forward differentiation is as efficient as one would expect. It's linear. The other differentiation, the other programs are also linear as long as you ignore sum types, and sum types give you a problem. So in any case, they're all space efficient. And if you happen to write a program encoding a DAG of operations, then you're a functional version of the usual backprop algorithm. So the only kind of slight fly in the ointment is the sum types, where you have a problem because computation goes apart and into different branches and it has to be brought back together again, and that causes you some issue. We'll come to that later a little bit. So this is a little very brief primer in context, which I guess everyone knows pretty well. So these are particular contexts, which I call environment contexts. So they're either a whole, or you let X be T in some other context. So here's a few little examples. So C is let X be 2 and then whatever. Y is let Y be 3 plus X and then whatever. So if you put D into C, you get let X equal 2 and let Y equals 3 plus X. And if you stick X times Y in that, you get something which evaluates to 10. If you do it the other way around, you get Y becomes 3 plus X, X becomes 2. And if you stick X times Y in that, you don't get a number, you get something which is 2 times 3 plus X. So that's a kind of illustration of how things go forwards and backwards, depending which way around you put the context. So let's, this is a little bit more in context. So if we wanted to, it's just interesting to look at how you type context. So we take this little context, let y be 3 plus x in whatever. Well, it's typed in an environment where x is a natural number, and the context binds y to a natural number. So write x colon that, a turnstile d, and then I put the binding in square brackets, as it were, in the hole, that y is a natural number. And there's a couple of obvious rules. So for example, well, these are both rules, all the rules. So if you want to type x becomes t and c, you type t, and then knowing that x is a type sigma, now you type c as gamma prime, then the whole thing is typed x of type sigma gamma prime. But notice I've got these square brackets after the x type sigma, and that's because the context might rebind x to some other type, so you have to be able to overwrite. So that's what that does. It's interesting to see how context and terms fit together from a typing point of view. So if a context C binds gamma prime, and you know this is all relative to some other gamma, and you know that gamma prime makes T have type sigma, then that should be a C at the bottom, then C with T is of type sigma. So you could rewrite that as saying that if C has the following type, if you give it something of type sigma, knowing that its arguments are of type gamma prime, then you get out something of type sigma. So you could see it as a continuation transformer. So we are using continuations after all, but at the meta level. And I won't go through the last bit there. Okay. So I want to illustrate how we do reverse differentiation. Well, this is without sum types. So let's suppose, this is all for T's normal form. So what we want to do, so suppose T's of type sigma, we want to reverse differentiate it. Well, we're going to feed it some gradient, a y twiddle of type sigma, because that'll be the tangent space of sigma if we don't have any sum types. And we want to output a context that binds all the input variables, the gradients of linear variables. So that's gamma twiddle. So the idea is if gamma is x1 sigma 1 and so forth, and gamma twiddle is x1 twiddle sigma 1 and so forth. But that's not quite accurate, because here we're thinking of everything in the kind of nonlinear world, and now we'll be in a mixed linear nonlinear world. And so the gammas are nonlinear, but the y's and the twiddly things are linear. And so we do use the usual trick of a kind of double context separated by a vertical bar. So a nonlinear on the left, the gamma, and linear on the right. So given now linear y will bind linear gammas. So you can see in the right-hand side, there's a kind of empty, because we're not thinking about binding any nonlinear variables, only the linear variables. And maybe it's a good point to say that the linear context will be a Cartesian, not multiplicative, because we don't need anything multiplicative here. So keep that in mind, otherwise things may look odd. Okay. So how are we going to use the context? As I already said, if we're going to do E then T, and E gives you some context C and D some context D, T some context D, then we'll just swap them. That's the kind of rough idea, but to get a little bit more precise, to get precise actually, here's the actual transformation. You might think I was going to give you the reverse source code transformation, but there's a bit of a twist. So let's call some other transformation, which I'm going to call I for intermediate. And so what the intermediate transformation does is, well, first of all, it calculates the primal. It says X becomes E. We're in a normal form, so E is going to be a typical elementary or atomic term. Then we're going to expect to get to bind the gradient associated to X. But as usual in these kinds of things, we're going to have to add up many contributions. So we start off with it set to 0. And then we do the context for T. And since that's got X in it, it'll bind X. So it'll bind X twiddle is what it'll do. And E needs the X twiddle, so we carry on and do E. The only reason to have an I and not an R is that we need to just see, if you see this I, it does local initialization of X, but we've got also a global initialization to do for any free variables of the whole program. And so R just does a global initialization, and it's at the bottom there of the screen. It initializes the X's in the gamma to 0. Okay, so now getting into a little bit more detail. Now, I somehow hope that I've explained the main ideas well enough, if far too quickly. So here's the source language. The source language is almost pretty well entirely what you'd expect, maybe with one slight twist. So there's a basic types, product types. I write them with brackets rather than times for some reason, and some types, sigma 1 plus sigma 2. And the terms are variables, constants, function applications, something odd, a local let x be t and u. We've already had for tuples and projections, components, and in left, in right, and cases. So the only thing to say is that these p's, so I said at the bottom, I call them decider terms. They seem like nice things to put in. So the decider term has a sum type b plus b prime. I could just have had booleans, then they would have been of some type 1 plus 1. But it seemed more general and fairly harmless. I won't say much about it in what follows. Okay. Target language is a lot more fun. It's going to have dependent types, like we saw before, in order to accommodate the variation in the tangent space. And it's going to have an odd elimination construct called a bunch construct, which actually was introduced by Nunes and Vakar and is essential to get the typing right. Okay, so the types are B or tuples or this cases thing, either. So depending what component you're in, according to T, so cases of T, you're either going to be, so T is either going to be in sigma, and then you're going to have some type alpha, which can be further dependent, might be some further sums in there somewhere, or Y, or it can be type tau, and then it'll be beta. So if you look in the example type there a bit further down the slide, if T is of type real plus a pair of reals, then its tangent space at T is cases T of, well, if it's actually in real, then tangent space is real. And if it's actually in a pair of reals, then tangent space is the pair of reals. Product, yeah, well, the space of pairs of reals. And we don't really need the X's and Y's because there's no further type with sums in there. Okay, so that's fine. So we have variables and there are different variables now, right? V, thinking of vectors, with zeros and sums. And where we had a function before, we now are going to be either forward or reverse differentiating with respect to a single variable. So we have a single, linear argument there in these functions. So f of non-linears t1 through tn in a single linear. All this would it would get worse in other circumstances, but here it's nice and simple. Won't bother about the p's, as well as the non-linear one let we have before. We now have a linear let. So let V be alpha in A and then carry on with A1. An interesting thing here is this T cases thing. So the idea is to have in your head this T and A. So T, if you think in terms of manifolds, T is a point in a manifold. And at that manifold point, there's going to be a tangent space and A is a vector in that tangent space there. That's a general idea. In terms of typing, a formal typing, T will be of type sigma, and A will be of, T will be of type sigma plus tau, and A will be of type cases T of X colon sigma something, Y colon tau something else. That's how that's going to work. I think that's everything in that slide. Here's how to type linear language. And then the thing that I've spent most time on since Paris in these several months is getting this to actually work. And you might expect, and you would expect, that you'd have, okay, you've got dependent types, so you're going to have type equality. And we're certainly going to have these new linear contexts. So they're going to need a gamma and a delta and bind some other gamma and delta. But we also need this subscript C. And the reason is best explained. These are the contexts as before. Why do we need these contexts? The idea is as you go down in the term, you're going to build up context by the nonlinear lets, which is fine. But it turns out you need to use the information that gives you to do the typing. So if you look at the middle rule there, for example, not for example, this is a critical one, then we want to type let x be t in A. Okay, fine. So to do that, we assume that X is of type sigma, delta isn't affected, and we say that we type A as being of type alpha. But the point is, when we come back downstairs from there, alpha had better not have X in it, but there's nothing stopping in the above part, alpha having x in it. So we need some way to get rid of x. So how can we get rid of x? Well, we happen to know that in that context, x is going to be equal to t, and t will be typed higher up. And even if there's some x higher up, it's a different x. So we could substitute t for x in the typing there of alpha, which in case it does have x in it, and that will produce a different alpha, which we can then put down to the bottom. So we have to use that information somewhere, and this is where the information comes from, and it's used in the typing rule for a particular typing rule for equality. So type equality relative to a C, and that rule is there. Though to see how it works, you'd have to have the rules for equality in front of you, which we won't have. So that's fine. Let's see. So for anormal forms, so I've just lost track of my timer here. That's better. Very little time as always. Anormal forms, obviously elementary terms and assignment. The target language, the anormal forms are just the things that would correspond to that. I think this is ignoring sums. So type translation, without types, the type translation from these are the idea of the type translation is given a type, is translate is a type is a tangent space, a dependent tangent space. So there's nothing to happening without some types. With some types, if you look at the bottom one there, the question is, what's the tangent space of sigma plus tau at the term t? Well, it depends what t is. So it's written by cases, and if it's in x, then it's the tangent space of x, sigma at x. Otherwise, it's the tangent space of tau at x, and you have to fill a bit with products. Okay, forward differentiation is exactly the same as before, but you have to take the dependency into account. So for example, if t is of type sigma, then f of t is of type, it's going to be the tangent space of sigma at t. So it's sigma twiddle sub t. Good. Forward differentiation. So I always write too much. So what interesting things to look at in this slide? Well, nothing too important. Given the time that's left, I can come back to the slide if people want. Reverse differentiation is, well, again, it's just exactly what we had before, except you have to make allowance for the tangent spaces. So for example, if t is of type sigma, then the gradient you'd want had better be in the tangent space of t at sigma twiddle. So the gradient is the sigma twiddles at t. Otherwise, it's the same. The gammas also are dependent on the gamma twiddles. For reverse differentiation, I would maybe point to the last line, and that's exactly what we had earlier when we were just talking more generally about motivation. It's exactly the same thing. I mean, actually modified by the dependencies. There's not really much to say about anything else really that isn't standard. So for example, if you want to reverse differentiate a function application f applied to some primal variables x's, you just do all the partial derivatives. For example, for x1, you update x1 by the partial derivative of f at y. This particular f is linear, so it doesn't need any of the primals. So there's nothing very much going on really. Transposition is, well, it's just a version of that. It's exactly the same, roughly speaking, exactly the same as the reverse, except you rub out all the twiddles. Instead of writing x twiddle, you write v for a variable. And so that's how that works. So for example, we want for the transposition of A, if it's bound, if it's typed in type sigma and its type is of type alpha, then as it were, going backwards, you'll come in with a V of type alpha and you'll bind the delta. So you just go exactly the right way around. There's no twiddles or anything because we're all linear now. Okay, and the translation, let's see, I wonder if there's some interesting things to say. So if you look at the second last line, then when you do a transposition on an assignment, on a let expression, you don't need to do anything with the primals any longer, because you're only interested in the linear part, and that's nothing to do with the nonlinear, the primal part. So you just transpose the A. On the other hand, if you're trying to transpose a linear let, then you do have work to do in both the M that you're letting and the body. So you do, and it's exactly the same as before, but it's linear. And I guess I don't want to say anything too much, given the time I've got left, about the rest. So this is introducing cases. We want to do forward differentiation. And it turns out forward differentiation is really easy as long as you use this bunch thing. So the forward derivative of a case is, so we want to look at y. So we're examining some y, but we want to know not only what the y is, but what the tangent is as well at that for the particular y. And then there'll be two different cases, and we can just use each of these separately. An interesting thing there is, you know, in some sense, you might be surprised there's nothing about cases in the target language. And this here, the top line there shows you what's going on. The f of in left of x is just x twiddles, because the tangent space of in left of x, the tangent space, so x is going to be a sum type. Excuse me, in left of x is going to be of some type, but in left, say sigma plus tau. But in left of x will be in the sigma part, which is exactly where x is. So the tangent space of in left of x at in left of x will just be the same as the tangent space of x. So that's why you can get away with that. A reverse differentiation. Oh, that's good. Coming back down with 12 seconds left. I just want to put, it's a very nasty giant thing, but I want to just give a slight feeling for what's going on. So when you reverse differentiate our cases, as you'll see, sorry. When you reverse differentiate cases, you have to reverse differentiate each of the branches, or you may have to. Each of these branches will give you a context which binds the variables in there, but to pass it out, and we have to pass that information out. So we evaluate some giant tuple, and then outside that, we look at all these elements of the tuple, and that just takes you more time, and that's where the lack of efficiency is. But it's only, well, it depends what your program's like, but it's to do with the number of variables that the cases do and the depth of the cases. So it's not too good and it's not too bad, and it's somehow life with cases is always hard. Okay, so one would like to do a lot more, but probably it's a good time for any questions. Thank you.